Hi, everybody. This talk is about Presto security, Apache Parquet column level access control with Presto. Um, a little bit introduction about myself and my colleague. I'm a tech lead manager at Uber Data Info, and I'm a Apache Parquet committer. My colleague Pevi, who will join me today to talk about the second half of this session. My team covers big data security and storage cost efficiency. We invest heavily in big data format, particularly in Apache Parquet. Parquet column encryption is the one that we spent a lot of effort in the last 2 years. We worked with the Parquet community and brought it up to the production. We roll out to Hive, Spark, and Presto, particularly for Presto, because it rewrites the Parquet reader. So we need to rewrite the Parquet column encryption. So that's why we want to give a tech talk today to the Presto community. We want to work with the community to merge the changes to the upstream. Other than the column encryption, we also invest in cost efficiency in Parquet. We adopted several hardcore technologies like column pruning to remove unused columns at the file format level, Z-standard compression, multiple column reordering, decimal precision reduction, etc. So all of these innovations working together make our data lake storage smaller and query faster. So we can find another time to talk about those topics. Today's talk is organized this way. First, let's talk about why we want to introduce Parquet column level access control in Presto. Then we will spend a little bit of time on Apache Parquet in Presto to set up the context. Hopefully, that can provide some help to understand the following contents better. Then we will spend most of our time to talk about Parquet column encryption and Presto column level access control through column encryption. Data masking is an important feature relates to the column encryption, and we will talk about that in the end. What do we cover and not cover? We will focus on the discussion of fine-grained access control in Hadoop data lake. We focus on the technologies other than the data itself. We will talk about open source technologies and internal tools like Apache Parquet column encryption, KMS, data masking, etc. But we're not covering all the aspect data security, and it's not a legal advice or guidance. First of all, why do we need column level access control or KLAC? In the following slides, we just call it KLAC. First, we want to protect data at the lowest level. Data lake, for example, HDFS, is an open system. The data can be accessed from many paths, Presto, Hive, Spark. People can even directly download the data. If you just provide access control at some path, it doesn't really protect the data. So KLAC encrypts the data at the storage. Regardless which path you get the data from, if you don't have correct permission for the key, you cannot decrypt the data. Secondly, it is for the fine-grained access control. We know coarse-grained access control at the table or file level doesn't work well for analytics tables. This is because in the typical data set, table usually have a lot of columns, but only a small percentage of the columns are actually confidential and need to be protected. To give example, we see a lot of tables that have hundreds of columns where only several columns need to be protected. So coarse-grained access control brings some problems for this scenario. Let's walk through the next slide. Let's do a comparison of use cases with and without KLAC. In the no KLAC scenario, example 1, example 2 are the results of no KLAC. Example 1, we have a select on 4 columns. The columns are A, ID, email, and B. Email and ID are highlighted in the red because they are considered as sensitive data. In example 2, it is a similar select, but this time the user is not actually trying to read any sensitive information. but it still gets denied because the permission can only be controlled at the table level. So in the bottom part, it is a KLAC enabled scenario. The same query are issued, and they are example 3 and 4. For example 3, the query is still rejected because they are trying to access the sensitive data but no permission. For example 4, since the user only select column A and B, which are not sensitive, user query succeed. So this will improve user experience while still protecting the data we want to protect. So we learned from the last example how KLAC uses scenarios. Now let's talk about the approach to implement that. The high-level approach is to enforce the access control at file format level. In our case, is Parquet. And encrypt only sensitive columns in Parquet and store the data in storage, which can be HDFS or cloud, which doesn't matter in this case. To access control to the data column is done by access control to the key. If you have permission to the key, you have permission to the data. Otherwise, it is access denied. So this is a very high-level approach. Let's get deeper into Parquet and see how we implement this approach. First, let's zoom in Parquet format structure for a little bit more details to build up the context here. Parquet is a column storage file format. The data in the same columns will be put together. That will make the data retrieve faster and data size smaller. Parquet is a popular big data file format, which is used very widely in Presto, Spark, Hive, and many other applications. So a Parquet file is divided into many row groups with a footer. The footer provides schema, metadata, etc., which is needed information when you read these Parquet files. Inside each row group is further divided into column chunks. So each column chunk is corresponding to a column in a table. Inside a column chunk is further divided into pages. So page is the unit for the encoding, compression, and encryption. Let's look into the column encryption flow for write and read. In this example, you have a table, just two columns. C1 is non-sensitive data and C2 is sensitive data. At the write path, also called the encryption path, a Parquet application, which can be Spark, Hive, or Presto, it invokes the Parquet library with column encryption support. And it tells it that the C2 is sensitive. Please encrypt it, and here is the key. Now, Parquet with the column encryption functionality, which is implemented in the Parquet 1178, will encrypt the data using AES and also store the key metadata along with the encrypted data and send it to the storage. When the data is sent to the air, it is encrypted. So you can imagine you get intercept in the middle in the air, it is still protected. The storage can be HDFS, S3, GCS, etc. So it doesn't make difference from the encryption perspective here. On the decryption path, when the Parquet file is read, the key metadata will tell the reader that the column is encrypted. Here's a clue to find out the key. The clue is the crypto metadata, which includes the key metadata like key index, key ID, key version, etc. that are with this information, the reader should be able to contact the key management service, or called KMS, to get the key and pass it to the Parquet library if user have the permission to the key. Parquet just decrypted. Now, if user doesn't have permission, the application will receive access denied exception or a masked value if you have data masking functionality. For data masking, we will talk about later. From the last slide, conceptually, the encryption and decryption is clear. But when it is rolled out to query engines to productions like Spark, Hive, Presto, you will find out several props need to be solved first. You need to define which column is sensitive and what key to be used to encrypt, and push that key to the Parquet library. What we find out is that it is convenient to just define those information along with the schema. So we extend existing schema for crypto settings and extend Parquet writer support to attach the crypto settings to Parquet schema and develop a crypto retriever as a plugin to activate the encryption based on the settings that we defined earlier in the schema. In the diagram, the application defines the schema with the encryption settings in metadata, or the application can read that crypto metadata from somewhere else, like metadata service, HMS. The extended Parquet write support will attach that setting to Parquet schema, and the crypto retriever will do the magic. It will build up the encryption properties needed by the Parquet and invoke Parquet API to do the encryption work. Parquet encryption has several options. You can choose whether or not encrypt the footer. Encrypt the footer will give you more security, but for the column level access control, all the people who need to access any columns, even for the plain text columns, they need to access the footer first. So that will add the complexity if you choose to encrypt the footer. For encryption algorithm, it supports AES GCM and AES CTR. GCM adds the integrity check on top of CTR. So in addition to preventing unprivileged reading, it also prevents malicious mutation to the original data. So it is more secure, but it adds more overhead, and you will see it is slower. Encryption with authentication. If you use AES GCM, you can optionally provide some additional authenticating data called AAD. If the unprivileged reader cannot provide the correct AAD, then it will fail. So it is more secure, but again, it will add more complexity. So you can choose the different options. Usually it's a trade-off between the security and the complexity and overhead. Now back to Presto. Presto supports several file formats, particularly for column file format, Parquet, and ORC. Presto rewrites Parquet readers for optimization, like nested column pruning, lazy read, predict push down, a lot of others. These are all great work, but as I said earlier, because of this rewriting, the changes we made for the column encryption in the Parquet library, which is Parquet MR repository, we need to be ported to the Presto Parquet reader. Here are the changes needed to support Parquet column decryption for read in Presto. First, upgrade Parquet format to version 2.7. Parquet format is a specification. Parquet MR, Parquet C++, and other Parquet writers or readers like Presto all follow the same specification. Column encryption feature in Parquet changed Parquet specification. So it needs to add several fields like crypto metadata, encryption algorithm, etc. So this change is released in Parquet format 2.7. Second change is to port column encryption changes from Parquet MR repo to Presto Parquet reader. As I mentioned earlier, because Presto rewrites the Parquet reader code, so we need the relative change in Parquet MR to be in the Presto Parquet reader. Currently, we are using Presto for reading data only, so we will start with the decryption first. So all the code changes we made has been rolled out to production for quite a while. They are pretty stable now. Because Presto will support ETL for write, we have a plan to port the encryption code soon. Keep tuned, please. The third change is implementation of the crypto property factory as a plugin. So in the previous slides, we talked about the crypto retriever, which is a plugin, and also a wrapper to shield all the encryption details, including wrapping up the KMS client, configuration for encryption properties, etc. So let's talk about that in the next slide. So Parquet 1817, it defines a crypto property factor, which is the interface. It is a common interface for loading file encryption and decryption. It makes encryption and decryption details transparent to analytics frameworks. And it leverages Parquet module encryption, which is Parquet 1178, with minimum changes. The relation of these components is described in this diagram. Presto as a service, and it has Parquet library. This library has the encryption functionality, which implements Parquet 1178. It implements basic building blocks for encryption and decryption. For example, AES encryption using the key that API passed in. Those APIs allow you to pass in the encryption properties, encryption keys, etc. That means your application code, in this case, Presto code, need to change to do all the dirty work and call the modified Parquet API to pass in those properties. Not just Presto, or other Parquet applications like Spark, Hive, etc. will need to do the same. So we decide to abstract to another layer as an interface, so that user can develop as a plugin. So that will be portable and can be shared across applications. So we implement this plugin called Crypto Retriever, and it is used for Presto, Hive, and Spark. It wraps up the KMS client details and the encryption settings like key metadata, encryption algorithm, configuration for the design options that we talked about in the previous slides. So all of these are wrapped up into a plugin and loaded by the different applications. Here are the status that we merge our changes to the Presto open source. Overall, the status is we just started. The first one is upgrade the Parquet version to 1.11, and the porting of the encryption code is tracked by the issue 12048. The decryption code change will be merged soon after Parquet version upgrading, and the encryption part is under planning. Now, I will hand it over to Pivy to talk about the KMS and data masking.
Okay.
I will stop sharing.
Are you able to see my screen?
Yeah, good.
Okay. Okay, so now let's talk about how we will manage the encryption keys, which are actually necessary to do the actual encryption and decryption. So first of all, the Parquet encryption implementation isn't actually restricted to any particular key management solution, and it's designed so any KMS could be used and plugged in to do the job of key management. The actual key metadata that's relevant to Parquet to encrypt the data is just a generic byte array, which maps to a key in any KMS. Basically, you're free to choose from the vast array of any KMS offering, and some examples include the Hadoop KMS, Ranger KMS, and several cloud KMS providers like AWS KMS and many others. Okay, now let's take a closer look at the integration between the key management and Presto. So this integration is controlled through a plugin which is added to Presto to support column encrypted tables. Essentially, this plugin is just a wrapper of a KMS client, and it's responsible for taking the key metadata from Parquet and retrieving the encryption and decryption keys from the KMS. It also has the job of serializing and deserializing key metadata into a byte array, which can be stored by Parquet. And lastly, the plugin controls additional encryption properties, like setting the encryption algorithm, like AES encryption, and different types of footer encryption modes. I want to highlight that all the key metadata required to read an encrypted Parquet file is stored alongside the encrypted data in the Parquet metadata. And this is important because it ensures that the encrypted data is never separated from the keys, and we never end up in a situation where you have encrypted data and you don't know which key should be used to decrypt it. And lastly, the KMS is important because this is actually how we control who gets access to what data. We basically set the ACLs on the key, and users are able to read data based on if they can access the key. All right, so what kind of performance overhead are we paying in order to get all these benefits of column level access control? So our performance testing indicates roughly a 5.7% write overhead and a 3.7 read overhead for column encryption. And if you break this down, it comes down to two parts. One part is the round trip time to retrieve the keys from the KMS. And the second part is the actual encrypting and decrypting time. And we found that the network round trip to the KMS was minimal in our case because of good caching and low latency corporate intranet deployment. And the majority of this overhead is spent on the actual encrypting and decrypting process. Also, I want to highlight that we tested this on a table with 60% of columns encrypted. And often you'll find that a lot of tables have a much lower percentage of columns that need to be encrypted. And this overhead decreases as a result of that. Okay, now I want to talk about some active work we're doing related to data masking. So what is data masking? Data masking is just the process of obfuscating sensitive data to users who do not have access to a column. And if this isn't completely clear what this looks like, don't worry. We'll look at some examples of data mask queries in the next few slides, which will make it more clear. So why do we need data masking? Basically, it potentially allows users to do useful things without compromising the actual content of the data. Additionally, it can improve the overall user experience of using column encrypted tables, because if a user tries to access an encrypted column which they don't have access to, we can give them masked values instead of rejecting the queries outright. Okay, so I'll go over the different types of masks and what they generally do, and then we'll dive into the pros and cons of each type of mask. So here are some of the masks that we're supporting right now. So first we have the null mask, which displays null values if a user doesn't have permission to a column. We have the hash mask, which can display pre-computed hash values. We have the redact mask, which can display predefined redacted data if the user doesn't have access. And then finally, we have user-defined mask, which allows table owners to define custom masks on their data. Okay, so what does the null mask look like? So here's an example on the right of a null mask query. So here we're selecting from some DB table, and we're selecting all the columns. And then the address column is considered sensitive, so it's bolded. And here in this query, we get back actual values for ID and language. And since the address column is sensitive and this user doesn't have access, they get back nulls instead. And the advantage of the null mask is really that it's very simple and it's the bare minimum of data masking. However, there's a few limitations, such as no joinability between masked data. There's possibility of confusion between real nulls and masked nulls. And there's an inability to support not nullable columns. Next, we have a hash mask. And again, we have a similar query, test query. And here we get hashed values as a result rather than real values. And again, so the big advantage with the hash mask is that now table joins are possible, even if the user doesn't have access to the column. So we can join between tables on the hashed values. And this allows users to do potentially useful things. However, there's some limitations, like this is an inefficient use of storage because we have to pre-compute these hash values and we have to store them alongside the data in the file. And lastly, we have the redact mask, which allows, on the right here, we have a query and we see that it allows the column data to be redacted so that you only see a portion of the values. And the big advantage here is that it's human friendly, but it's not really usable for joins. We can't really support all types of data. So this makes a lot of sense for string values, but it might not make sense for like Boolean values. And it's an inefficient use of storage because we have to pre-compute this. All right, here we have some usability design considerations that we're taking into account as we roll this out. The first thing is that queries are run by both humans and machines. So data mask queries, when we're designing data masking, we have to take into account that not all of our users are humans, and this affects our design. Another thing we have to be cognizant about is that communicating the mask values versus real values. For example, a null mask, the user needs to know if this is a null resulting from a mask or if it's a real null. And we want to make sure we avoid surprising users as much as possible. And this comes into play when we're rolling out. We want to make sure as we roll out, users aren't surprised by these null values or masked values. Okay, to recap, column level encryption enables fine-grained control of your data sets. We control permissions through the KMS by controlling ACLs on the keys. All the Parquet encryption details are wrapped up in the Parquet code, as well as the Presto Parquet implementation. Data masking is currently in POC and we're rolling it out. And we're merging all of this, the merge to open source Presto is underway. And lastly, we're hiring, and you can feel free to apply on this link if this kind of work is interesting to you, or forward your resume to Shinli. So I think we have a minute to do questions now.
Yeah, there's one question that hasn't been answered. If you can just take a look at that one. Is encryption of columns on each individual value or a whole block of values as a unit? And the second part of the same question is key rotation supported?
Yeah, that's a good question. So it's actually a block of values. And that's actually an important point, because if it was each individual value, there could be problems, or there could be concerns about like encryption between two values that are the same, allowing like some sort of attacker to be able to correlate values. But since it's a block, we kind of avoid that concern. And then for key rotation, yeah, KMS supports key rotation, and you can set up processes to regularly rotate your keys every week or something like that.
Yeah, just add a little bit about the first one. The encryption is happening in the page level. So the page is a unit for encoding, compression, and encryption in Parquet.